Okay, we're starting with chapter 10, part 2. Okay, in this problem here, we're told we're practicing ideal gas law. Calculate the volume occupied by 0.845 moles of nitrogen gas at a pressure of 1.37 atmospheres and temperature of 315 Kelvin. So our number of moles, well, what we want is volume. We don't know what it is, but it's going to be in liters, right? And the number of moles is 0.845 moles. And then we're given, let's see, a pressure of 1.37 atmospheres. And temperature will be 315 Kelvin. So doing a quick inventory of PV equal nRT, we do have a pressure. Volume is what we're looking for. Number of moles we have. We don't have R. I'm going to add R here. R is equal to 0.0821 liters times atmospheres over mole and K, right? So now we have R and then we have T. Let me work this out here. So our equation is PV equal nRT. We're trying to solve for V. So we want to isolate V by dividing both sides of the equation by P. We have V equal nRT over P. Okay, so number of moles is 0.845 moles. And then times 0.0821 liters times atmospheres over mole times K. And then times temperature is 315. This question is near perfect in the sense that you don't have to convert anything, right? And then the pressure is what? 1.37 atm. So our goal is to get volume in liters. So all the units should cancel out except for volume. Moles and moles cancels out. ATM cancels out. Kelvin cancels out. The only thing that is remaining is liters. So let's go ahead and work this out. I'm going to type this in. I'm sorry I'm not sharing my screen when I'm doing the math. It's just going to be a lot of screens, right? So I'm going to do 0.845 times 0.0821 times 315 divided by 1.37. Okay, so I get 15.9. Okay. Let's see what they got. 15.9. Yeah, 15.9 liters. Okay. Great. So this problem here is a little bit different in the sense that it is still ideal gas laws, but the values given to us are not in the desired unit. We're still using PV equal nRT. Let me see if I can work it out right here. I don't know if I'm going to have enough room. I'm going to have to add a page. So let me go ahead and just add the page right now so I don't get boggled up by that detail. Okay. So we asked to calculate number of moles. So what is wanted here is some amount of moles, right? Of a gas in the 3.24 liters. So we're given volume 3.24 liters. Basketball inflated to a total pressure. We have a pressure that is 24.3 psi, right? And then we have a temperature that is 25 degrees Celsius. And then we have a value of R that is 0.0821 liters times atmospheres over mole times K. Okay, so what I'm going to do here is convert this. Let me use this area up here for conversion, and I'm going to replace all these with the numbers I want. A pressure of 24.3 psi can be converted to atmospheres, which is what I want. 14.7 psi is 1 atmosphere. So when we divide this, what do we get? Once again, doing my math on the side. 24.3 divided by 14.7. I get 1.65 atm. So let me actually go ahead and replace this with the units I want, 1.65 atmospheres. Okay, so the first one is done. This is done. Volume is fine. I don't have to convert that. Temperature from 25 degrees Celsius, I have to add 273 to get 298 Kelvin. So go back down here and replace that with 298 Kelvin. Okay. We're looking for number of moles. So our equation is going to be PV equal nRT. Divide both sides by RT to get the moles by itself. And I'm going to flip this over so it says number of moles is PV over RT. Okay. So our moles are going to be 1.65 ATM. I just used that one. My volume is 3.24 liters. I just used that. And I put this in there. I'm going to put in R. R is 0.0821 liters times atmospheres over mole times K. And then temperature here is going to be what? 298 Kelvin. 298 Kelvin. Okay. So let me go ahead and work this out. I have 1.65 times 3.24 divided by 0.0821 divided again by 298. And this gives me what? 0.219 moles. Is that correct? Of nitrogen? Is that what they get? Oh yeah, look at that. 0.219 moles of nitrogen. Very good. Okay. So I'm moving on to the standard conditions. So when I was in school, I was learning about standard conditions in the chapter of gases. And I was like, oh, I got this. We covered this in thermodynamics. It must be the same thing. So the one thing I want to mention is the thermodynamics. So right here, or thermochemistry. In thermal, for standard conditions, we tend to deal with solutions. So for one, we're dealing with solutions. And the solutions had a concentration of 1 molar. And if there was a pressure involved for solids, liquids, or gases, the pressure was at 1 atmosphere, right? In that chapter, the temperature, standard conditions temperature was 25 degrees Celsius. And if there was moles, the number of moles was essentially 1 mole, okay? In the chapter of gases, though, you want to be aware that we don't deal with solutions. We only deal with gases. So I'll say here, we deal with gases. And with gases, the pressure will be 1 atmosphere, so it does match. The temperature, though, here is 0 degrees Celsius. So I just kind of glossed over this information. When the teacher was talking, I was like, I got this. And of course, I didn't get it. And I started getting questions wrong, and I was not very happy with that. Moles will be 1 mole. So just be aware of this critical difference. Temperature is different. Okay? So sometimes you will see problems where they're saying, there is a certain gas or nitrogen gas at STP. When they say STP, they're saying standard temperature and pressure. Now, if the problem gives you a pressure value, go with that. If they don't give you a pressure and don't give you a temperature, and they just kind of leave that as a blank and they tell you STP, then you want to fill in the temperature is 0 degrees Celsius, and then the pressure will be 1 atmosphere. Then you will need those numbers from the understanding the standard temperature is 0 degrees Celsius and pressure is 1 atmosphere, okay? So hopefully that makes sense. Okay, the next thing we're going to be looking at is the density of a gas. So we can go ahead and figure out the density of a gas from the ideal gas formula. Density of the gas has a unit grams per liters. Density is mass over volume. So I'm going to show you how they use the rearrangements to pretty much get density from Pervner. Now, for those of you who are going to minor in chemistry or take minor in chemistry or take additional classes beyond organic chemistry, you will have to know how to rearrange this equation yourself. So PV equal nRT. Remember that number of moles is going to be mass over mole. Well, I'll put it here, MM for molar mass, right? This one here stands for molar mass. And then we're also told, remember that density is mass over volume. Okay, I write the volume as V. Okay, So we're going to go ahead and replace this moles here with this equation and say PV equal mass over molar mass times RT. And then I want to bring the volume down. So I'm going to bring the volume down by dividing both sides by volume, right? And so now we have P equal mass, and I write the volume as V, and then RT over MM, right? But we want the mass over volume by itself because that pretty much makes up the density. Actually, let me change this to density because this stands for density. And density has a symbol D. So I'll put D here, and then of course I still have RT over MM. So to get the density by itself, multiply both sides by the inverse of this relationship. So molar mass over RT, molar mass over RT, and then this cancels out, kind of like dimension analysis. And now we have density, the subject, equal to pressure, molar mass over RT. Okay, and this is the equation we use to find the density of a gas. So if you're looking for the density of a gas, once again, the density has a unit grams per liter. You want to know this. Don't gloss over this information because it does help to guide you when you get lost. Pressure will be in atmospheres, right? So that's the units. Molar mass has a unit grams per mole. And then R has the unit liters times atmospheres over mole times K. And then temperature has Kelvin. All these units map into each other, right? Atmosphere, atmosphere, liters, liters, grams, grams, moles, moles, Kelvin, Kelvin. They all map into each other to allow dimensional analysis to do its wonderful work. Okay, let's go ahead. Now that we've worked that one out, we're told from the relationship that if its density is related to pressure, molar mass, R and T, then density is directly proportional to molar mass because they have that numerator relationship. You all see that? Remember, the density is a default a numerator, and molar mass is also a numerator. Since they have that direct relationship, they're going to be directly proportional to each other. That means if the density goes up, the molar mass goes up also. Or you can say the molar mass goes up, the density goes up. Okay? Let's see how this plays out in an actual problem. So we have a problem right here. Let me see if I can add a page to the problem. Add a page. In our problem right here, we're told, calculate the density. So what we want here is density. I like capitalized D. So gram per liter, that's what we're looking for nitrogen gas. So for nitrogen gas, I have to get the molar mass. One nitrogen is what? 14. The molar mass here would be 28 grams per mole. So we got the molar mass from the formula. Okay. Temperature. Temperature is 125 degrees Celsius. Convert this to Kelvin plus 273. That should be 398 Kelvin, right? Because it's 125. Okay. And the pressure of 755 millimeters of mercury. So we have pressure 755 millimeters of mercury. What is this going to be? Let's figure this out. It's 755, not 775, right? So we got 755 divided by 760. That gives us 0.993, 0.993, okay, atmospheres. Okay, so we need R. R is 0.0821 liters times atmospheres over mole times K. Oops, I combined that. It's mole times K. Okay, density formula is pressure times molar mass divided by R and T. So pressure here is, let me zoom this out so I can see my numbers. Oh no, cancel. What is this? Cancel. Let me write on this side. 0.993 ATM times 28 grams per mole divided by 0.0821 liters times atmospheres over mole K times 398 K. Okay, we know that since we're trying to get density, we should have grams over liters left, right? not canceled out. So ATM and ATM cancels out. Moles and moles cancel out. K and K cancel out. We're left with grams, right? And liters. So since our number is going to be some number grams per liter, that will be a density. Let's do the math. We have 0.993 times 28 divided by 0.0821 divided by 398. And we have 0.851 grams per liter. Okay, let's see what we get over here. Okay, 0.852. It's the way they rounded it up. But we got it. Check. We can move on. We have another practice problem, but this time they're saying that they want us to find what? Let me go ahead and add a page here so we can solve this problem. Add a page. Remove this. Okay, in this problem here, we're told a sample of gas has a mass. So we're given mass of 0.311 grams. Its volume is 0.225 liters. So we got mass and volume. The temperature is 55 degrees Celsius and pressure is 886 millimeters of mercury. Okay. So temperature is 55 plus 273. That makes 328 Kelvin. Pressure is 886 divided by 760. This is 1.1658 atmosphere. Okay. And so what are they looking for? Find the molar mass. So we're looking for molar mass, which should be some number grams per mole. Okay. Now these two numbers here give us a density. Let's go ahead and just get the density over and done with. The density will be 0.311 grams divided by 0.225 liters. That should be equal to 0.311 divided by 0.225, 1.382 grams per liter. Okay. We got this. Now let's go ahead and do this. So we're looking for molar mass, right? We know density equal pressure times molar mass divided by RT. We're looking for molar mass. So to rearrange this, we get molar mass equal, multiply both sides by RT. Let me erase this part here and do it step by step like I've been doing. I'm kind of rushing through this one, trying to get to the end of this. Oh, and then divide both sides by pressure. Divide both sides by pressure. So doing the inverse, right? So we get molar mass equal to dRT over P. So what is our density? 1.382 grams per liter times, maybe I can move this over to the left because I'm using up a lot of space. Okay. Times R, right here. 0.0821 liters times atmospheres over mole K. So we did this and this. Temperature, 328 K divided by pressure, 1.1658 ATM. Is that what I got? 1.1658. Okay. Let's see how the units play out. If the units don't work out, there's no point in doing the math, right? So let's see. We got liters and liters canceling out. ATM canceling out. K cancels out. We're left with grams over moles. Yep, it works out. So our answer for molar mass will be some number grams per mole. Now we can commit to the math. Let's see how the math plays out. The math should work out because the units did work out, right? Theoretically. 1.382 times 0.821 times 328 divided by 1.1658. Okay, we get 31.9 grams per mole. Okay. And this was for a sample of a gas. So let's go ahead. The gas might be oxygen because oxygen is 32. Let's see what they get. Look at that. Doesn't that feel good? I hope it feels good that you got it right. They had a different approach, but I hope it feels good. Okay, so now we're starting with this part right here where we're looking at a mixture of gases and partial pressures. So we're told here many gas samples are not pure but a mixture of gases. For example, the gas that we're breathing right now, air. Dry air, for example, is a mixture containing nitrogen, oxygen, argon, carbon dioxide, and a few other gases in trace amounts. In certain applications, the mixture can be thought of as one gas. By knowing air's pressure, volume, and temperature, the total moles of the molecules in the air sample can be determined, even though they are different compounds. Okay? So this is air, the composition of dry air. And we're told that air is made up of 78% nitrogen, 21% oxygen, 0.9% argon, and 0.04% carbon dioxide. So it would be like saying the total we haven't gone over the law yet. Look at me getting ahead of myself. Air is made up of all of these gases, right? So then we come into Dalton's law of partial pressure. Remember Dalton from before? Yes. He is that scientist that told us about the atomic model, the first one that we covered, I want to say years ago, weeks ago. He's back. And this time he's giving us a law that kind of sounds obvious. But in this law, he's saying that when you have a mixture of gases, what is the partial pressure? What's the total pressure? His law is called Dalton's law of partial pressure. The pressure of a single gas in the mixture of gas is called its partial pressure. So in my studies, in my journey of learning chemistry, I learned that whenever the term partial is used, that implies whatever chemical you're talking about is part of a bigger picture, right? It's part of a whole. So the individual gas in the mixture of gases is called partial, indicating that there's more than the one you're studying. This is just part of a bigger picture, right? Partial pressure. The sum of the partial pressure of all the gases in the mixture equals the total pressure. This is known as Dalton's law of partial pressure. So instead of looking at generic gas A, B, and C, I want to go back here and talk about this. So what Dalton is saying is that if you have a mixture of gases, right, to figure out the total pressure of all those gas mixture, the pressure total in this case for our air will be the pressure of air, right? Because air is essentially a mixture of all those gases. To get the pressure total of air or pressure of air, take the partial pressure of nitrogen, add it to the partial pressure of oxygen, add it to the partial pressure of argon, and added this to the partial pressure of carbon dioxide. You don't just call them pressure of oxygen, pressure of nitrogen, you don't call it pressure of nitrogen, pressure of oxygen, pressure of argon, pressure of carbon dioxide, because in the world of chemistry, if you just say pressure of nitrogen, you mean that you don't have a mixture, you just have nitrogen by itself. But when you say you have a partial pressure, you're indicating nitrogen is part of a mixture of gases. Does that make sense? Right? So take the partial pressure of nitrogen, partial pressure of oxygen, partial pressure of argon, partial pressure of carbon dioxide, add all of these up and you get the pressure of air. Okay. So there's one more thing I want to add before we get into the actual math. Okay. So for this part here, we're told that the gases behave independently. So what do they mean by that? They mean that when you're measuring the partial pressure of nitrogen, so let me try to copy this over here and add this to, okay, I thought I was copying. Okay. Let me copy this. Copy. And add this to this blank page. So we're being told here that these gases in the mixture behave independently. So nitrogen, oxygen, argon, and CO2 behave independently. My spelling is horrible. Okay. Yeah, that's correct. Okay. In what ways and how does that influence how we get the partial pressure? Okay. The partial pressure, I'm going to write the partial pressure of each of these, right? So because they behave independently, they occupy this is how it plays out, by the way. They behave independently by occupying the full volume in container. So that's how we see them exert their independence, by occupying the full volume of the container. Wait, what? What they're saying here is that when you look at the volume of nitrogen in a container where there's a mixture of gases, the volume of nitrogen gas in that container is the volume of the whole container. Just because the other ones are so small, all the gas particles occupy almost no space. So the other ones, it's almost like the container is empty. Okay. So to make this simple, when you're writing the ideal gas equation for nitrogen, to get the partial pressure of nitrogen, you have P for nitrogen, V for nitrogen, equal N for nitrogen. R is for everybody, T for nitrogen. Then we can say that the volume for the nitrogen gas is pretty much the volume of the container, so we don't have to specify nitrogen here. It's just the volume of the container is in. And then it just so happens that the temperature of nitrogen gas will also be the temperature inside the container, so we don't have to specify this part right here. So the part that's unique to nitrogen will just be the pressure and the number of moles. Okay? So many times when we're trying to find the partial pressure of nitrogen, the partial pressure of nitrogen will be equal to, let me write the symbol differently. I'm getting a little distracted. Pressure of nitrogen is equal to number of moles of nitrogen, RT over V. Okay? So if I want to take this equation here and then recreate this pressure total, then I can say the pressure total, which is essentially the pressure of air, pressure total, is equal to, for nitrogen, I'll write number of moles of nitrogen, RT over V. Remember, this takes the place of partial pressure of nitrogen. And I'm going to add this to number of moles of oxygen, RT over V. This takes the place of partial pressure of oxygen. Okay. Then I'm going to write number of moles of argon, RT over V. This takes the place of partial pressure of argon. Then finally, I'm going to write number of moles of carbon dioxide, RT over V. This takes the place of the partial pressure of carbon dioxide. Okay. So in a gas that's part of a mixture, the part of that gas that is unique to that gas is its partial pressure and its number of moles. R is common to all the gases in the mixture. The temperature is just the temperature of the environment that's common also. The volume for each gas is also common. Okay, the only part that's unique is the number of moles and, of course, the partial pressure. So I'm going to go ahead and move on. I kind of shortened the slide, so I'm going to, I kind of mentioned this part already, so I'm not going to go over it again. How does this play out in the lab? For those of you taking this class on campus, you're going to be generating hydrogen gas in your last experiment. And the hydrogen gas, you're going to be doing something similar to this, not exactly like this, but similar to this, where you'll be collecting the gas, the hydrogen gas over water. So we're being told here, gases are often collected by having them displace water from a container. The problem is that water evaporates to form water vapor. There is also water vapor collected. Oh, okay. The problem is that because water evaporates, there is also water vapor in the collected gas. Okay. So what they're saying here is you're going to be doing the experiment. And when you do the experiment, you're going to be generating hydrogen gas. The hydrogen gas that's going to be generated will be similar to the setup we have right here. Not exactly like this, but very similar. The gas will actually travel from the site where it's generated, okay? And it will travel into water. And the idea here is this container will be set up before the gas gets generated. And initially, this whole part here will be full of water, okay, to make sure we don't have anything else in there but water. We don't want to have an unknown, a third gas that is unknown. As the hydrogen gets generated, it will come in here and displace the water. So push the water out as the gas gets generated, okay? Well, as the water moves down and is being displaced, water vapor will remain here. So if I zoom in and you see the picture right here, I want to highlight the water vapor. So you see that? You have water vapor here. So we have our intended gas that we care about. That's the hydrogen gas. But we also have water vapor. So in the end, we actually have hydrogen gas plus water vapor. Remember the law of a mixture of gases? That is Dalton's law of partial pressure. So Dalton's law says here that we have two gases, a partial pressure from the hydrogen gas that we were actually creating, the dry hydrogen gas, but then we also have a pressure being generated by the water vapor. So this is the water vapor. So when you add these two pressures, you get a total pressure. Okay. Now, for those of you who are doing this experiment on campus, please notice that the total pressure will also be equal to the atmospheric pressure. So atmospheric pressure. So you will have to measure the atmospheric pressure in the lab for us to know what the total pressure is. Okay. So we want to see how this equation here plays out. Total pressure equal pressure of hydrogen, the dry hydrogen, plus the pressure of water. So we're told here, a table can be used to find the partial pressure of water vapor. Oh, so we can find this number here from a table. Where's the table? You will see it in a moment. When collecting a gas over water, example, a gas sample is collected over water. Okay, pause. Since the gas is collected over water, what we're saying here is the pressure of that gas sample that we're making will be added to the pressure of water to get the total pressure. Okay, continue reading. The gas sample has a total pressure. You see how this plays out? Total pressure of 758.2 millimeters of mercury. Okay, so we know P total equal P gas plus P water. Okay, so we're told that P total is 758.2 millimeters of mercury. So we got this one here. From the vapor pressure of water table, we're told the temperature was 25 degrees Celsius. From the vapor pressure of water table, the partial pressure of water vapor is 23.78 millimeters of mercury at 25 degrees Celsius. Okay, let me scroll down for a moment, y'all, so you can see what they're talking about. Oh, look at that. There's a vapor pressure of water versus temperature table. There it is. Once again, in chemistry, the table is like a buffet. It's information for us, tools for us to solve problems. You want to scroll. The temperature here is related to the vapor pressure. You want to scroll and find your temperature. They told us the temperature was 25 degrees Celsius, right? So find 25 degrees Celsius right here, and then read the pressure. That pressure is the pressure of water vapor. So 23.78. So I'm going to go back here and say the water vapor is 23.78 millimeters of mercury. So can we find the pressure of the gas? Of course. Pressure of gas equals 758.2 millimeters of mercury minus 23.78 millimeters of mercury. And what do we get? 734.4. Let me double check. I'm just copying these. Sorry, y'all. I'm getting a little bit tired. 758.2 minus 23.78. 734.42 millimeters of mercury. So we got what they got. I was copying, but it works out. Okay. That is how you will use the table. The table is here to provide you the vapor pressure of water, which you need to subtract from any from any pressure, any gas that is collected above water. Okay. You need to have the temperature though, because you won't know what to read without a temperature. So you have to have it in Celsius, because all of these are in Celsius. Please notice that, right? They're all written in Celsius. Okay, let's work on this next problem right here. We're doing good, guys. We're doing good. I'm mostly encouraging myself to hang in there. Okay, let's work on this next problem right here. I'm going to add a page and then we will work on this. In order to determine the rate of photosynthesis, the oxygen gas emitted by an aquatic plant is collected over water at a temperature of 293 Kelvin. So we got temperature 293 Kelvin. And the total pressure is equal to 755.2 millimeters of mercury. Okay, so we said oxygen gas emitted by an aquatic plant is collected over water. So remember, total pressure here, so P total will be P oxygen plus P water, just FYI. Okay, let's keep reading. A total of, 1.02 liters of gas. So we have a volume, 1.02 liters of gas is collected, right? So I got the temperature, I got the pressure total, and I got the volume total. What is the mass of oxygen gas? What mass of oxygen gas in grams forms? Okay, so what is wanted here? I know I wrote all over the place. Is grams of oxygen. Okay, so of course we're going to need R. R equals 0.0821 liters times atmospheres over mole times K. Okay, remember how I told you guys that when you're trying to find the partial pressure of oxygen in this case, the pressure of oxygen is unique to oxygen. Number of moles of oxygen is unique to oxygen. Then we have R, T, right? And then V will be like that. Okay, that's the equation we're working with. So let me do a quick inventory and see if we have everything we need. Actually, let me move this to the side. Do we have everything we need? Quick inventory, checklist, right? We don't have pressure of oxygen. We have pressure total, but that's not pressure of oxygen. For us to find pressure of oxygen is equal to pressure total minus pressure of water. Okay, so pressure total is 755.2 millimeters of mercury. And then pressure of water, I have to read the temperature. Oh, so this has to be converted to Celsius, right? So minus 273 equal 20 degrees Celsius. So I need to go to the table and read 20 degrees Celsius. I'm going to go to the table back here. 20 degrees Celsius, that's 17.55. So I'm going to go down here and say this is going to be minus 17.55 millimeters of mercury. Okay, that gives me the vapor pressure of water. So 755.2 minus 17.55. I guess 737.65. While I'm here, let me go ahead and convert this to ATM. So divide by 760, and I get 0.97 ATM. Okay, so I can finally say my pressure of oxygen is done. It's been a minute, but it's done. Okay, I don't need this number anymore. I don't need the calculation anymore. Those were all a means to an end. I need R, right? So R I have and I need. Temperature I need and I have, and then volume I have. So I can get number of moles of oxygen, right? So I probably need to rearrange this. So number of moles of oxygen is equal to pressure of oxygen volume over RT, right? So pressure of oxygen will be 0.97 atm. That part is done. Times volume. Volume is 1.02 liters. That part is done. Divided by R. R is this number right here. 0.0821 liters times atmospheres over mole K times. What's my temperature? 293. 293 Kelvin. Okay. Okay, oops, 0.97 times 1.02 divided by 0.0821 divided by 293. Okay, I get 0.0411 moles. But they wanted mass, right? Yeah, mass in grams. I know. I've written all over the place. I'm sorry. Is this one of those problems that requires all that? Does it need all that? Yes, it does. In this case, it needs all that. Okay. So I'm gonna write moles equal mass. Make sure you know this formula by heart over molar mass. So mass equal 0.0411 times, what was the gas again? Oh, oxygen. Oxygen is 16 times 2, so 32 grams per mole. And this one here is going to be mole, right? So mole and mole cancels out. So our answer will be in grams. What do I get? Times 32, 1.32 grams of oxygen. Okay. Let's see. We have that. They converted it to ATM. 1.32 grams of oxygen. Great. Then we're moving on to kinetic molecular theory of gases. In kinetic molecular theory of gases, the postulates are, by the way, this is describing the ideal gas. Remember the ideal gas that goes with the ideal gas law, Pervnert? That's the gas. This is the simplest model for the behavior of gases, talking about gases as particles that are in constant motion. The gas particles are very tiny, they travel in straight lines, and we have little to no attraction between the particles. So we're told the attraction between the particles are negligible. You can almost say no attraction because it's so small between the particles. Moving gas particles hit another gas particles or the container, and they do not stick together because they have elastic collisions. They bounce off and continue moving in another direction, not losing energy, as though the collision never happened, right? There is a lot of empty space between the gas particles because the density is very low compared to the size of the particles. So remember, this is where if you're trying to figure out what space the particle occupies or what space is available for the particle to travel, it's the whole volume of the container because gas particles behave as though they don't take up space, at least the ideal gas particles. Okay. The average kinetic energy of the gas particles is directly proportional to the temperature in Kelvin. We mentioned this before. You want to make the gas move faster, increase the temperature. You want to have a linear relationship. You want to track Kelvin temperature. Okay, so I'm going to move on from here. Now we're looking at stoichiometry. Okay, this thing is in my way. I'm trying to find a place where it's not going to be in my way. I don't know where to put it. Okay, down here, I guess. Okay, this is reminding us stoichiometry. We're like, wait a minute, stoichiometry, yes. Every time the author wants you to remember it, he shows you the mass to mass conversion. Okay, so the mass to mass conversion, that's what we have right here, right? Grams given, moles given, moles wanted, grams wanted. This is periodic table conversion, balanced equation, and then PT. So we've covered this before. So the nice thing about using the iPad is I can just pick a different color. Okay. Then we went to liters. No, that was a different color. Why didn't they like my choice? Maybe I was pressing the wrong thing. Okay, the color of the marker. Oh, there it is. Liters given. And we go to moles given. The moles given, balance equation, moles wanted, and then we go to liters wanted. So we know the conversion here is molarity. This is going to be molarity here. And then we also did what? We did a molecules. Let me do a different color for that one. Molecules. For molecules given to moles given, that would be Avogadro's number. And then from here to here, also molecules wanted. Also Avogadro's number. Okay. The one we also did in lecture that kind of took a different turn will be from grams given to kilojoules. That one kind of detours here in the middle, so that'll be kilojoules wanted. So essentially, you'll be going from the left and then going over here like that. Okay. Now we have a whole new path. Our last and newest path. I want a vibrant color. Do you want to do pink? Is pink bright enough? I want something that's loud. Sure, why not? Let's make this. This is going to be pervness. So when you're looking at pressure, volume, temperature, you use ideal gas law, PV equal nRT to do the conversion. And same thing over here. Then you do P, V, and T. You're going to use PV equal nRT. So what's the purpose of the stoichiometry, right? Let me go over here so this doesn't look as confusing. In this section here, oops, no, I want to go back to the red color. Stoichiometry helps us get moles of wanted in gas chapter. Okay. Okay. So how do we know what path we're going to take? Most of the time, you would start from the given, grams given, you go to moles given. And then from moles given, you go to moles wanted. And then from moles wanted, you go down this path here to find that. Or you might do the reverse, right? So grams given to moles given, moles wanted, and then you're either finding pressure, volume, or temperature. Hopefully that makes sense. Okay, let's see it play out, because it's one thing for me to stand here and talk about it. It's one thing else. It's something else for us to actually work it out. Okay, so in this problem here, let's see how the problem plays out. Add a page. Okay, so I'm going to go ahead and copy the equation because we're doing stoichiometry. So I'm going to copy the equation so I know what's what. Now I'll just write it down. Okay, so we have CO gas, 2H2 gas to give us CH3OH gas. Okay, methanol can be synthesized by the reaction below. What volume in liters of hydrogen gas? Stop. Come over here. What is wanted is the amount volume in liters at a temperature of 355. So temperature here is 355 Kelvin and the pressure of 738 millimeters of mercury. They're talking about hydrogen, right? Do we need to synthesize 35.7 grams of methanol? So this is 35.7 grams of methanol. Okay. So of course I asked this question in the class, right? In lecture. What is our given? What's our wanted? And those are pause, but here's the easier way to find the given and the wanted. The wanted is usually the more obvious one because that's what you're solving for something in the wanted. Ergo, why it's called the wanted. So this is the wanted because I have a W here. That's going to be your wanted. Your given may not have more information, but it tends to have more complete information. There's no question marks in the given. That makes this a given. Why is it important for us to identify that? Because we want to always start the stoichiometry from the given and then end up with the wanted. So we have to know what's the given, what's the wanted. Does that make sense? Okay. So I'm going to start with the given, 35.7 grams. And the chemical is CH3OH. Okay. So in stoichiometry, when you start with grams, the next conversion always has to be PT. Almost always, unless it's in the end and then you might go to something else. But in this case here, if you're starting with grams, next conversion PT. So what is the molar mass of CH3OH? CH3OH. H is 1, O is 16. This is going to be 3 times 1, and this is going to be 12. So let's see. This and this is 15, and then 16. So we have 32, right? Okay. 32 grams of CH3OH, 1 mole CH3OH. And then what comes next is mole, no molar mass, mole to mole ratio. So balanced equation relationship. It shows here for every 1 mole or 1 amount of CH3, 1 mole of CH3OH, we have 2 amounts or 2 moles of H2 from the balanced equation, right? I think that was it. That was it for this part here. Because the purpose, I told you guys before, right? The purpose of the stoichiometry is to find the moles of wanted in the gas chapter. This is essentially the moles of the wanted because the moles of the given is right here, right? So we can get moles of H2 so we can have enough to use permanent. Let's set this up and see what we get. 35.7 times 2 divided by 32. 2.23 moles. Okay, so now we have number of moles of hydrogen as 2.23 moles, right? So if we have all this information here, can we go ahead and find the volume of hydrogen? Okay, let's see. Let me transfer this below. So for hydrogen, we have a temperature of 355 Kelvin. So just move this over, right? I'm going to move the information in the way I want it. The pressure, I move over 738. But I'm going to divide by 760 to get atmosphere because I want to just get it over and done with. 738. Ooh, 738 divided by 760. This is going to be 0.97 atmospheres, okay? So I move this over. The number of moles is 2.23, okay? Moles. And then R, of course, is R, 0.0821 liters times atmospheres over mole times K. How do I know I need R? And remember, we're solving for volume. That's what we're solving for, to get liters. Because if you do an inventory of PV equal to nRT, you see we have the pressure right here. We're looking for the volume. We have the number of moles. Now I have R, and then I have T. So let me rearrange permanent. PV equal nRT, V equal nRT over P. So N is what? 2.23 moles times R, 0.0821 liters times atmospheres over mole times K times T, 355 K over P, 0.97 ATM. 2.23 times 0.0821 times 355 divided by 0.97. Because of the way I rounded up, I get 67 liters. Okay. I kind of had to look to see what they got because I was like, this number doesn't look familiar. Okay. If you round this up, you get 67. It's just the way I rounded it up, right? But that's what you get right there. So we got it. Whew. Okay, last little section right here, and then we're when I say we are done, I mean I am done, right? I'm so close to being done. Okay, so we just saw how ideal gases behave. Now we're looking at real gases. Now we're told that that's the reminder that says I should get ready for bed. Real gases often do not behave like ideal gases. So here's the thing. Let me back up a little bit. Gases can behave ideally if the condition allows for them to behave ideally. It's the same gas that will either behave ideally or behave like a real gas. So what exactly is a real gas here? It's a gas that will be under low pressure, high temperature environment. Okay, so let me add a page here to kind of itemize this a little bit so we can be more technical or more intentional about this. Okay, ideal gases. Ideal gases prefer low pressure environment because in low pressure environment, the particles remain far from each other and intermolecular force of attraction is low. Okay, so they like low pressure environment because of that. The next thing they like is high temperature environment. Why high temperature? Because when the temperature is high, they tend to be very fast and energetic, fast moving. Okay, because they're fast moving, they have time to slow down and form intermolecular forces of attraction because they're moving fast. They collide with each other, and then the walls of the container maintain that pressure, and then they travel in straight line. But the temperature has nothing to do with that. But let me see, what did I write down here before? Oh, they're free. And they're free in moving around. And that has to also do with the attraction being low, right? So after we see that, then we can see that if you have these two conditions here, low pressure, high temperature, this facilitates the existence of ideal gas, okay? So then how do we get the same gas to behave like a real gas? Just do the opposite. Real gases will then, the same gas will behave more like a real gas, which is more of a reality, if you just reverse the condition. So you flip the condition and have high pressure and low temperature. So why high pressure and low temperature? Why does this affect the gases? Because in high pressure, the gas particles are now forced close together, right? So we have a greater intermolecular force of attraction. And when that happens, we see that the gas particles now, what is affected here is the pressure of the particles. So the pressure of the particles is affected because you don't have the gas particles getting to the wall of the container and colliding a lot, right? They don't get to the wall that much because they spend more time getting attracted to other particles. So they are not making it to the wall. And sometimes when they get attracted, they're moving together, moving a lot slower. Imagine you're running a race by yourself versus you're in a three-legged race. When you're in a race by yourself, you're moving a lot faster, right? Because you have more freedom. There's nobody weighing you down. In a three-legged race, you're kind of attached to somebody else. So then the two of you have to move together really fast. So when the gas molecules are drawn to each other, attracting each other, it slows them down. And when this happens, it kind of slows them getting to the wall and hitting the wall, right? So the pressure is affected. So we'll see later on when we're looking at the ideal gas equation, the pressure gets affected. Okay, so I'm back to this one here. The next thing we see is when you have high pressure, low temperature, the same thing. The molecules move very slow, so now they're able to attract each other, right? And then not only that, scientists noticed the size of the real gas particles is actually a lot bigger than what was hypothesized, what was thought of in the ideal gas law. So the volume that's available for the gases to move around is lesser than what was predicted. It's lesser? It's lower? It's lower? Okay, let's go with lower. It's lower than that which was predicted by the ideal gas law. So here we're told, because real molecules take up space, the volume of a real gas is larger than predicted by the ideal gas law. at high pressure. At lower temperatures, the pressure of real gas is less than that of the ideal gas. I told you guys why, right? All that interaction and attraction between the particles slows them down. They don't get to the wall of the container that much, and the pressure is now lower. At the lower temperature, the gas atoms spend more time interacting with each other and less time colliding with the walls, right? Making the actual pressure less than that predicted by the ideal gas law. So when we combine all these factors, remember the beautiful PV equal nRT equation we had before? That gets altered because we now have to consider all the different things that make the real gas real, right? We have to correct this factor right here, correct the pressure with this factor because of the intermolecular forces, and we have to correct the volume with this factor here because the particles are now a lot bigger than what they estimated. So our nice, straightforward permanent equation becomes this beautiful thing, okay? And with that, the chapter is over. And not just the chapter, we finished Chemistry 1411. Thank you very much for joining me in this journey. I really hope that your next step in chemistry will be a great one. If this is your last class in chemistry, once again, thank you for joining me, and I'm wishing you all the best in your future classes. Okay. It is my bedtime now, so y'all, it's been great.